Welcome, future psychologists. Today, we're going to demystify a core statistical tool that helps you answer a massive question in your field.
This is the big one, isn't it? How on earth do we take a small, manageable study and then make a confident claim about a much, much larger group? Well, hypothesis testing is the bridge that connects that small sample to a really big conclusion. So, to answer that big question, we first need to get a handle on the fundamental challenge that all researchers face. Look, the challenge is pretty straightforward. We can't study everyone. We have to work with a small sample to try and understand the whole population. And the z-test, that's our tool for deciding if what we found in our sample is a genuine discovery or if it's just a random fluke.
Okay, so before we can see if her sample is anything special, we need a map of what normal, or expected even, looks like. In stats, we call this map the distribution of sample means. Just imagine for a second that you could take thousands, millions even, of samples of the exact same size from a population. If you calculated the average for every single one of those samples, and then plotted all those averages on a graph, you'd get this, the distribution of sample means. It's literally our map of every possible outcome. And here's where a little bit of statistical magic comes into play, the central limit theorem. This amazing theorem tells us that it doesn't matter what the original population looks like, as long as our sample is big enough, our map of sample means will form a predictable bell curve. And that predictability, well, that's our secret weapon.
So this map follows three really simple rules. First, its center is the exact same as the true population average. Second, its variance, or its spread, gets smaller as our sample size gets bigger, which makes sense, right? More data means less guesswork. And third, we can always find its standard deviation. These rules make our map predictable and incredibly powerful. Okay, we have our map. Now let's add two crucial tools to our kit that will help us navigate it. This is our compass. The standard error tells us the average distance between any one sample mean and the true population mean. So a small standard error means our sample is likely a really accurate snapshot. A large one means there's a bit more guesswork involved. And this just makes intuitive sense, doesn't it? This is exactly why those big, well-funded studies with thousands of participants are often way more reliable than small ones. The more data you collect, the clearer the picture becomes, and the smaller your standard error gets. All right, we've got our map, we've got our compass, and we understand the rules of the road. Now it's time to actually use our main tool, the z-test. I know, a formula. But don't let it scare you. All this is doing is asking a simple question. How far away is our sample mean from the population mean? And it measures that distance in units of standard error. That's it. It's just telling us how many standard steps away our result is from the average. To make sure our conclusions are totally sound, we follow this 5-step process. We'll state our ideas as hypotheses, figure out our comparison map, decide on the cutoff for what counts as special, calculate our sample score, and then finally, make a decision. Let's just walk through these steps with an example. So here's our scenario, and we'll follow those 5 steps. A social psychologist wants to know, does hearing that someone has a positive personality actually make them seem more physically attractive? So, following our process, we know the population mean for attractiveness is 200. But our sample of 64 students gave an average rating of 220. Is that 20-point jump a real effect, or is it just random chance? To find out, we have to calculate our z-score.
Okay, first we calculate the standard error. We do that by dividing the population standard deviation, which is 48, by the square root of our sample size, 64. That gives us a standard error of 6. Now we just plug everything into the formula. 220 minus 200 divided by 6. And that gives us our z-score, 3.33.
So what does 3.33 even mean? Well, remember step 3 of our process, finding the cutoff score? In psychology, that cutoff is typically 1.96. Our score of 3.33 is way bigger than 1.96. That means our result is so far from the average that it's extremely unlikely to be a fluke. We can reject the idea that there's no effect and conclude that personality does make a significant difference. Great, we have a significant result. But how do we talk about it professionally? And just how certain are we about that effect? In a research paper, you report your findings in a clear, standardized way.
You state the conclusion, and then you provide the proof. That P stands for probability, and P is less than 0.05 is the scientific shorthand for saying the probability of our result being a random fluke is less than 5%. It's the gold standard for statistical significance. You know, the z-test tells us if there's an effect. A confidence interval gives us our best guess for how big that effect is. For our example, we could be 95% confident that the true average attractiveness score for people hearing about a positive personality is somewhere between 208 and 232. It gives us a plausible range for the real-world effect.
You've made it through the core concepts of one of the most fundamental tests in psychology. So let's just quickly talk about where you go from here. Look, it is crucial to understand how the formula works, but in your day-to-day research life, you are not going to be doing this by hand. Software like Jamovi and JASP will crunch the numbers in seconds. Your real job as a future psychologist is to understand what those numbers mean. And if you're sitting there thinking, whoa, that was a lot, that's completely normal. I promise you, every single researcher on the planet has been exactly where you are now. Confidence in stats comes from practice and repetition, not from getting it perfect on the very first try. You've absolutely got this. Keep practicing with different examples, stay curious about the questions behind the numbers, and you'll soon see statistics, not as a hurdle, but as your most powerful tool for making real discoveries.